Hey class, so this is Kathleen here. I'm going to go over these last couple problems in case you missed it because we had some problems with the internet. So I'm on lesson 1.6, page 3, looking at problem C. We're trying to figure out the end behavior of this function. And so we look at dominant terms. The square root of 2x squared would be the dominant term in the numerator. 3x would be the dominant term in the denominator. Simplifying this numerator, it's square root 2. The square root of x squared is the absolute value of x. All right, so let's take a second and look at that. Why is that? Think about if you have the square root of -3 squared. Is that equal to -3? No. It's equal to +3 because when you have square root, you always do the absolute value. You always get the positive root. So this is equal to the absolute value of -3. So the square root of x squared is always equal to the absolute value of x. All right. In order to take this limit as x goes to infinity, I need to understand something about this absolute value of x over x. So let's take a second and look at that function, the absolute value of x over x. If that was my function, what would that graph look like? And if we take just a few values and a little chart, point plotting, sometimes that's a great way to figure out what's going on. Say I plug in 8, absolute value of 8 over 8 would be 1. Say I plug in 7, absolute value of 7 over 7 would be 1. Whatever I plug in positive, I would get 1. What happens if I plug in 0? I can't divide by 0. Oops, can't do that. The function's going to be undefined at 0. Now let's try some negatives, like -2. Absolute value of -2 over -2 would be 2 over -2, which is a -1. What if I try -5? Well, that's the same thing as this one. It's going to give me the absolute value of -5 over -5. So 5 over -5 is -1. So this graph is always 1 for positive x, and it's always -1 for any negative x value. And at 0, the function's undefined. So that's a really funky function. That's the graph of the absolute value of x over x. So if you're wanting the limit as x goes to infinity of the absolute value of x over x, if I think about this graph, it's always 1 for positive x. If I wanted the limit as x goes to -infinity, it's always going to be -1. All right, so let's use that back in my problem here. So I need the limit as x goes to infinity of the square root of 2x squared plus 1 over 3x minus 5 to see what the end behavior of this function is. This is what is modeling the end behavior. The absolute value of x over x is going to 1, and so I have root 2 over 3 is my limit. If I'm looking at the limit as x goes to -infinity, all right, again, this function models the end behavior of the function. As x goes to -infinity, the absolute value of x over x is going to -1. So this limit will be minus root 2 over 3. So I have two horizontal asymptotes, y equals root 2 over 3, and y equals -root 2 over 3. So that's kind of a tricky problem. This next one is a little bit tricky as well. Again, I want to think about what function models the end behavior. The dominant term in the numerator is 5x. The dominant term in the denominator is square root of 9x fourth. Simplifying that denominator, I have 3x squared. So I can, and I don't need absolute values here because x squared is always positive. So here I had to have absolute values when I did the square root of x squared, but the square root of x4 is just x squared. All right, that would simplify to 5 over 3x. So again, this is the function which is modeling the end behavior for me. So I'll take the limit as x goes to infinity. I know it feels like, man, I'm writing this a lot, but you can't just write limit of nothing. It has to be the limit of something. So the limit of that function, I'm thinking about this as x goes to infinity. I have 5 over infinity. Any constant over infinity, the limit's 0. If I do the limit as x goes to minus infinity to figure out that's happening at the other end of the function, again, I'm thinking about this function as x goes to minus infinity. So it's 5 over 0, 5 over minus infinity, but 5, any constant over n and infinity is 0. So I have a horizontal asymptote of y equals 0. All right, so let's put all this together, what we learned in the last lesson about finding vertical asymptotes and what we've learned in this lesson about finding horizontal asymptotes. The limit as x approaches 4. In the numerator, I would get 16 minus 36. That'd be a negative 20. In the denominator, something bigger than 4 minus 4 is 0, but it's always positive because the values I'm plugging in for x are a little bit bigger than 4. All right, so anytime you have a constant over 0, I know the limit is either positive or negative infinity. Since this is a negative value, because negative divided by positive is negative, this limit's minus infinity. All right, here, again in the numerator, I'd get negative 20, but this time, since I'm approaching 4 from the left, the denominator would be approaching 0, but it'd always be negative values. Well, negative divided by negative is a positive, so this limit's positive infinity. As x goes to infinity, I've got infinity over infinity, so I'm looking at dominant terms. So I look, this is about equal to x squared over x, which is x. The limit as x goes to infinity of x is just infinity. Here, x squared over x, of course, is just x. As x goes to minus infinity, this limit is minus infinity. All right, so horizontal asymptotes. Again, we find those by looking at what happens as x goes to infinity or minus infinity. Well, there's no asymptotes. This is still important information. It tells me about the graph, but it also tells me there's no horizontal asymptotes. Vertical asymptotes, as x goes to 4, the function's going to infinity or minus infinity. So x equals 4 is a vertical asymptote. We can use this information to do a quick sketch of the graph. All right, here at 4, I'm going to have an asymptote. So, oh, sorry, there we go. I'll draw that in. As I approach 4 from the right, it should be going to minus infinity. So I know which direction. I know it looks something like that. As I approach 4 from the left, it should be going to positive infinity. So I know it should be something like that. As I go to infinity, it goes to infinity. So this increases without bound. As I go to minus infinity, this goes to minus infinity. It decreases without bound. That gives me a quick little sketch of the graph. We're going to do another little sketching problem on page 4. This time the limits are all already given to you. You're not being asked to find the limits, you're just being asked to sketch the graph. All right, so I'm looking here. The limit as x approaches 3 from the right. I'm going to see, oh yeah, here's another one. 3 from the left, 3 from the right. One goes to infinity, one goes to minus infinity. So I've got a vertical asymptote at 3. Approaching 3 from the right, it's going to infinity. 3 from the left, it's going to minus infinity. Let's see what else I got. The limit as x approaches -2 is minus infinity. Oh, -2, notice that's a two-sided limit. So on either side of 2, it's going to minus infinity, and so that's an asymptote. So I know the graph would need to come down like this. Now I don't have any other information about what's happening between -2 and 3. So I just need to join these two pieces so it's a function that's defined everywhere except at those asymptotes. You can draw it way up here, you can have it come down, but bottom line, somehow they connect, and here it's going to minus infinity, and here it's going to minus infinity. All right, so I still need to do this one. The limit as x goes to infinity is 3. That sounds like a horizontal asymptote. So it's approaching 3. As I go to minus infinity, it's also approaching 3. But notice I'm down here this time, so it's going to be approaching 3 from below it, it looks like. And so just make that kind of a smooth curve approaching 3. All right, that's the end of that lesson. Hope that helped, guys. See you in class.